In this video, we'll develop the Viterbi algorithm in detail for this example. And if you've seen dynamic programming, that's exactly what we're doing. So here's our trellis diagram with the two probability tables, emission and transition. Let's draw this a bit larger with all the probabilities. Recall that on each node we have the emission probability, so that's the probability that the particular part of speech generated the word above. And on the edges we have the transition probabilities, which are the probability that we get from one state to the next one. For clarity, we've removed the edges that have probability 0, but we still consider them. And now the idea is that for each state or dot in this diagram, we'll record the maximum probability of all the paths that end in that dot and generate the words that are above. So let's start from the left. The probability that the word Jane is generated by the path that ends at the top end node is the product of the probability of getting to that node from the start node, which is 3/4, times the probability that the node generated the word Jane, which is 2/9. This product is 1/6, so we'll record it. Likewise, the probability on the M node is 1/4 times 0, which is 0. And the one on the V node is 0 times 0, which is 0. Now let's go to the next word, will. There are 3 paths that end in the top right end node. One coming from the previous N, one from the previous M, and one from the previous V. We need to look at the 3 and pick the one with the largest probability. The probability for the path coming from the N node is 1/6, which is the probability so far until the word Jane, times the transition probability 1/9 to get to the new N node, times the emission probability 1/9 for emitting the word will. We'll record this product as 1/6 times 1/9 times 1/9. Likewise, for the path that comes from the M, the probability is 0 times 1/4 times 1/9. And for the path that comes from the V, it's 0 times 1 times 1/9. Since 2 of these are 0, the largest one is the first one, which is 1/486. So we'll record that number as the probability of the highest probability path that ends at that point. And this is important. Of the 3 incoming edges, we'll keep the one that gave us the highest value. So that's this blue edge over here. And we'll delete the other ones. If 2 edges give us the same value, that's completely okay. We can break ties by picking one of them randomly. Now we'll continue this algorithm, and feel free to sing along with it or pause the video if you'd like to do the calculations in detail. For the M node, the competing probabilities are 1/6 times 1/3 times 3/4, 0, and 0. So the winner is the first one, which is 1/24. And again, we keep the blue edge since it gave us the highest value. For the next one, it is 0, since the 3 of them are 0. Here we can keep pretty much any edge, since they all give us the same value. Since it's 0, in order to prevent cluttering, let's actually not keep any of the edges. We'll continue doing this in the future when we get all zeros. And we continue over each word, always calculating the 3 probabilities coming from before and taking the largest one. And remembering which edge gave us the largest value, keeping that one and removing the other ones. And now we have our probabilities, and also our edges that get us to those probabilities. So how do we get our optimal path? Well, we start from the end and trace backwards. Since each state only has one incoming edge, then this should give us a path that comes all the way from the beginning. And that path is the winning path. This gives us the chain of states that generates the observations with the highest probability. And that's how we conclude that the most likely tags for this sentence are noun, modal, verb, and noun. And these are correct, so our hidden Markov model did a great job. And as you notice, we didn't need to check 3 to the 4 paths. We only needed to label around 3 times 4 nodes, which is much faster.